Welcome back. It is genuinely good to have you here with us. Today, I want to start by asking you to do something a little different. I want you to visualize something. Picture the last printed circuit board you worked on. Maybe it's sitting on your desk right now, covered in probes, or maybe it's up on your monitor in your CAD tool. What do you see?
I know what most people see. They see the components.
Yeah.
They see the MCU, the regulators, the connectors, the LEDs. They see the stuff they spent weeks selecting from DigiKey or Vouser. They see the things that cost money.
Exactly. We look at the bill of materials. We look at the placement. We obsess over whether that capacitor is too close to the edge of the board or if that USB connector is going to align perfectly with the enclosure cutout. We focus entirely on the things we can touch. But today, we're going to talk about the thing you can't really see once the board is fabricated. We're talking about the invisible component.
And arguably, it is the most important component on the entire board if you care about signal integrity or electromagnetic compatibility. We are talking about the board itself, the layer stack-up.
It's funny because we often treat the PCB as just a holder, a mounting bracket for the real electronics. Like it's just a slab of fiberglass that keeps the parts from falling on the floor. But the reality is the stack-up is the backbone of the physics.
It is the foundation. If you get the stack-up wrong, honestly, you can have the most beautiful symmetrical component placement in the world. You can have the most expensive low-noise regulators money can buy, and you will still fail your EMC testing. You are fighting a losing battle against physics.
That is a terrifying thought, that you could doom a project before you even route the first trace, just by picking the wrong layer configuration in the setup menu. So that is our mission today. This is episode 7 of the EMI Control podcast. We're going to master the choice of layer stack-up to outperform in EMC.
It's a natural progression from where we've been.
We talked about where to put components.
We discussed partitioning. We discussed the absolute necessity of not splitting your reference planes in a way that creates dipoles. But that was all about surface geography. It was about where things sit on the map.
Today, we are going vertical. We are moving from the XY axis to the Z axis. We are slicing into the board to see what's happening between the layers.
And this is a crucial pivot. In episode 6, we kept saying, don't split your ground plane. That's a great rule. But today, we explain why you need that plane in the first place and exactly where it needs to live vertically in the stack to actually do its job.
We're going to walk through this logically. We'll start with some core physics that might actually surprise you, or at least correct some bad habits we all learned in school. Then we'll tackle the humble 2-layer board, move up to the versatile 4-layer, and finally get into the high-performance 6-layer configurations.
And we're going to have to break some myths along the way, especially about power planes.
Oh, the power plane debate. I'm
Yeah.
looking forward to that. But before we get into the layer counts, we have to talk about propagation. I love how our source material puts this. It breaks down the physics of how a signal actually moves.
For a signal to propagate, it requires a loop. It requires 2 conductors.
2 conductors. So conductor A is the trace I draw in Altium or KiCad. That's the easy one. What is conductor B?
Conductor B is the return path, the reference.
Which we usually just call ground.
We do, and honestly, that terminology, calling it ground, is where 90% of engineers get into trouble.
Why? Ground is ground, isn't it?
Yeah.
0 volts. The dirt outside.
Ground implies a magic bucket. It implies a place where current goes to disappear, or just a static 0-volt reference point that exists everywhere simultaneously. But in the context of signal propagation, the reference conductor is an active participant. It is half of the transmission line. The current has to go out on the signal trace, and it must come back on the return conductor to close the loop.
So if I send 10 milliamps out to an LED, 10 milliamps has to come back.
Precisely. Kirchhoff's laws don't stop working just because the frequency goes up. The current always returns to its source. The million-dollar question for EMC is, which path will it take?
And this is where the frequency matters, right?
It matters immensely. At DC or very low frequencies like audio or a simple battery power current takes the path of least resistance. It's lazy. It finds the shortest, fattest, most conductive copper path back to the source.
So if I have a big copper pour, it just draws a straight line through it.
Basically, yes. It spreads out, but the bulk of it takes the path of least resistance. But as soon as you have high-speed signals, and by the way, with modern rise times on chips, almost everything is high speed now, regardless of your clock frequency, the rules change. The return current no longer cares about resistance. Resistance is negligible. It cares about impedance, specifically inductance. It takes the path of least inductance.
Least inductance. Okay, that sounds a bit more abstract. Geometrically speaking, on a circuit board, where is the path of least inductance?
It is directly underneath the signal conductor.
Directly underneath, like a shadow.
Exactly like a shadow. The return current wants to be as close to the signal trace as physically possible. Why? Because that minimizes the loop area. When the forward current and the return current are right on top of each other, their magnetic fields cancel out. That cancellation lowers the inductance.
So if I have a trace on layer 1, the return current is desperately trying to flow on layer 2, right underneath that trace.
Exactly. It will crowd underneath that trace. And this brings us to why we use planes. A plane is a continuous sheet of copper. It offers infinite possible paths. Because it's continuous, the current can perfectly mirror the signal trace above it. It creates that path of least impedance automatically.
Versus a trace.
A plane solves that geometry problem for you. It says, here is copper everywhere, take the path you need.
This connects back to what we said in the last deep dive about splits in the plane. If I have a trace on layer 1 and the current is flowing on layer 2, and suddenly I put a cut in layer 2.
You've destroyed the bridge. The current hits that cut. It can't jump across the gap. So what does it do? It has to go around. It has to find the nearest piece of copper that connects the two sides of the cut.
So instead of a tight loop underneath the trace, I now have a massive detour.
You have created a large loop area. And in electromagnetics, a large loop is effectively a loop antenna. You are now broadcasting your signal to the world. And conversely, you are receiving every piece of noise from the world into your signal.
So the goal of the stack-up, fundamentally, is to guarantee that the return path is never broken.
Correct. Discontinuities degrade signal integrity, meaning your ones and zeros get messy, maybe your timing is off, and they increase leakage, meaning you fail your EMI testing.
This leads us to what the source material calls the golden rule of stack-up design. It seems pretty simple on paper, but I have a feeling it's harder to execute.
The rule is deceptively simple. Match every signal layer with an adjacent return reference plane, or RRP.
Adjacency, that's the key word.
It is non-negotiable. You cannot have a signal layer, then another signal layer, and then your ground. That's too far. The fields need to couple immediately to a reference. That adjacency is what contains the electromagnetic fields within the dielectric material between the layers. It's what keeps the energy inside the board and not radiating out into the lab.
So if I have a signal on layer 1, layer 2 must be a reference.
Ideally, yes.
Okay, so we've got the theory. Signal plus reference equals propagation. And they need to be neighbors. Before we start applying this to actual board counts, because I know everyone wants to know how to fix their 4-layer board, I think it's important to give credit where credit is due. These aren't just abstract rules we're pulling out of thin air.
No, absolutely not. These are physics-based engineering principles.
This deep dive is actually provided by Frezou Electronics. We're working off the material from their EMC EMI design course.
Right. And the insights we are breaking down today come directly from Dario Frezou. He's a principal engineer and a serious specialist in this field. What I appreciate about his approach, and you see it in the source material, is that he bridges the gap. You have the academic physics, which is often dense and theoretical and hard to parse. And then you have the frantic, I need to ship this product by Friday reality.
Yeah, it's very practical. It's not assume a spherical cow in a vacuum. It's do this, don't do that, and here's exactly why.
Exactly. It's engineering discipline. And if you want to go deeper than we can go in an audio format, you really should check out frezouelectronics.com or look at the Frezou Electronics Academy. It's where you go when you stop guessing.
Absolutely.
Yeah.
Okay, let's take that discipline and apply it to the hardest challenge of all, the 2-layer board.
Ah, yes, the 2-layer board. It sounds like it should be the easiest, right? It's just top and bottom. Less to manage, it's cheaper to manufacture.
But according to the source, it's actually the most difficult configuration for EMC. Why is that?
Because you have zero room for error. You have extremely limited real estate. In a 2-layer stack-up, if we follow our golden rule signal adjacent to reference, we have a problem. We have 2 layers. If one is signal, the other must be reference.
Now, that means I have to dedicate one entire layer to be a solid ground plane.
Ideally, yes. Layer 1 is for components, signals, and power routing. Layer 2 is a solid, unbroken sheet of copper.
But come on. In the real world, signals have to cross. I mean, unless you have the simplest circuit in the world, you eventually run out of space on the top layer. You encounter a trace crossing another trace. You feel this intense urge, this temptation, to just drop a via, route a little bridge on the bottom layer to jump over the obstacle and pop back up.
And that is the trap. That is exactly where the 2-layer design falls apart.
Walk me through the physics of that mistake. I route a signal on the top. I need to cross another signal, so I drop to the bottom, which is my ground plane, run a trace for maybe half an inch, and come back up. What did I just do?
You just cut the return path for every single signal on the top layer that happens to cross over that little half-inch slot you made on the bottom. Remember, the return current for the top layer is flowing on the bottom layer. It's flowing in the copper. If you turn a piece of that bottom layer into a signal trace, you have removed the copper. The return currents on the top layer are flowing along, happy as can be, referencing the plane below them. Suddenly, they hit this moat your jumper trace. They can't cross it. They have to flow all the way around the end of your jumper trace to get back to the other side.
You've created a massive loop just by adding a tiny trace on the bottom.
Yes. And suddenly, your radiated emissions spike, and you have no idea why. Because the schematic looks fine. You look at the schematic and say everything's connected, but the physics is broken.
So is the advice never route on the bottom?
The advice is be extremely disciplined. If you must route a signal on the return layer, keep the crossing as short as physically possible. And this is critical. Check your vertical alignment.
What do you mean by vertical alignment?
Do not allow a signal trace on the top layer to cross over the area where you put a signal trace on the bottom layer. If you have a trace on top crossing a trace on bottom, you have a signal crossing a gap. That is the worst case scenario.
So if I put a cut in the ground plane, I have to make sure the sky above that cut is empty of signals.
Exactly. It requires a lot of manual checking. You have to visually inspect the board in 3D in your head. Okay, I cut the bottom here. Is anything crossing on top? No. Okay, I'm safe. But if something is crossing, you have to move it.
It sounds like a headache.
It is. That's why two-layer boards are so hard. You are constantly fighting the urge to use layer 2 for routing, but physics demands you keep it solid.
Which is probably why most people eventually say, forget it, I'm going to 4 layers.
Exactly. When the density gets too high or the routing gets too complex, you simply cannot maintain a solid ground plane on a 2-layer board. You have to upgrade.
So let's talk about the 4-layer stack up. This feels like the workhorse of the industry. Probably, 70% of the boards I see are 4-layer?
It gives you that breathing room. But even here, you can mess it up if you don't understand the stack-up choices. Just adding layers doesn't automatically solve EMC.
The source mentions 2 main configurations for a 4-layer board. Let's start with what they call the standard approach. This is probably what most people default to.
The standard approach, or configuration A, is layer 1, signal, layer 2, return reference plane, ground, layer 3, return reference plane, ground, and layer 4, signal.
Okay, so signal on the outsides, 2 grounds in the middle.
Yes. This is a very robust design. Think about our golden rule. Layer 1 is adjacent to layer 2, perfect reference. Layer 4 is adjacent to layer 3, perfect reference.
And the middle, where the 2 grounds touch.
The middle is where the 2 ground planes meet. This is actually great for thermal spreading and just lowering the overall impedance of your ground net. But from a signal propagation standpoint, the beauty is that your outer layers are perfectly shielded from each other by the inner core. It's what we call embedded planes. The signals are exposed on the outside, the reference is on the inside.
But there's a second configuration, the shielded approach.
This one flips the script. Layer 1, return reference plane. Layer 2, signal. Layer 3, signal. Layer 4, return reference plane.
So ground, signal, signal, ground. You've buried the signals inside the board.
Correct. We call this the shielded approach because the outer layers act as a Faraday cage. They shield the internal signals from external noise, and they prevent the internal signals from radiating out. It's a high-performance configuration, often used in noisy industrial environments or RF designs.
But wait, I see a problem here. If layer 2 is signal and layer 3 is signal, they are next to each other.
You spotted the risk.
Doesn't that violate the rule? Where's the reference?
Well, layer 2 references layer 1, the top ground, and layer 3 references layer 4, the bottom ground. But you are right, layer 2 and layer 3 are adjacent. And that creates a risk of crosstalk.
Crosstalk meaning the signal on layer 2 couples to the signal on layer 3 instead of its ground plane.
Exactly. If they are too close, the electric and magnetic fields will bridge between the 2 signal layers. They will talk to each other. And that corrupts your data.
So how do you fix that?
You have to play with the z-axis geometry. You need to increase the vertical space, the prepreg thickness between layer 2 and layer 3.
Push them apart.
Push them apart physically. And simultaneously, you use a very thin dielectric between layer 1 and 2 and between layer 3 and 4. You want the coupling to the ground plane to be much, much stronger than the coupling to the other signal layer.
That makes sense. It's all about managing the fields. You make the path to ground easy and the path to the neighbor hard.
Precisely. You control the physics by controlling the thickness of the fiberglass.
Now, regardless of which 4-layer config you pick, the source mentions something called stitching vias.
Yes, stitching vias are essential.
I always visualize these as like staples, just stapling the ground planes together around the edge of the board.
That's a good visualization. You are connecting all your ground pore areas and planes together with vertical vias. This does three things. First, it completes that Faraday shield we talked about. It closes the cage at the edges.
Like the bars of a cage.
Right. The spacing between the vias determines the highest frequency you can block. If the gap is smaller than a fraction of the wavelength, the wave can't get out.
That's cool. What's the second thing?
Second, it keeps the planes at the same potential. You don't want ground on layer 2 to be at a slightly different voltage than ground on layer 3. That difference creates noise. Stitching creates an equipotential structure. It turns your separate planes into one massive block of ground.
And third.
Return paths for layer transitions.
Oh, right. We talked about this.
If a signal jumps from layer 1 to layer 4, the return current has to get from layer 2 to layer 3. It can't fly through the fiberglass dielectric. It needs a via.
So if I don't put a stitching via there, what happens?
The return current has to wander off looking for the nearest ground via. Maybe it's an inch away. Maybe it's at the power supply connector. It creates a massive loop.
So the rule is, place a via right next to your signal via when you switch layers.
Keep the return path tight. You should almost treat them as a pair. Signal via, ground via.
Okay, now I have to ask about the elephant in the room for 4-layer boards, the power plane.
A power plane warning.
Yeah. I feel like almost every basic tutorial I saw in college or even early in my career was signal, ground, power, signal. That was the standard 4-layer board. You dedicate layer 3 entirely to 5 volts or 3.3 volts.
So this source material is very explicit about this. Don't do it.
Really? That feels so convenient. I have a whole plane for power. I can tap into it anywhere. It makes routing so easy.
It is convenient for routing, absolutely. It makes the layout engineer's life easy. But it is dangerous for EMC in a 4-layer stack-up.
Why?
Think about the structure. Layer 2 is ground, layer 3 is power. You have 2 large plates of copper separated by a dielectric. You have formed a parallel plate capacitor.
Isn't capacitance good for power?
It creates high-frequency interplane capacitance, which it can be good, but noise on the power plane can easily couple into your signals. More importantly, a power plane often doesn't act as a good return reference for high-frequency signals in the same way a ground plane does.
Why not?
Because the power plane is full of noise. It has switching noise from your buck converters, ripple from the mains. If you reference your clean signal to a dirty power plane, you are injecting that noise directly into your signal.
And the source mentioned common mode noise.
Yes. It creates common mode voltage noise that drives the whole board structure against the chassis or the cables attached to it. It's a recipe for failing radiated emissions.
So in a 4-layer board, where does that power go if I don't have a plane?
You route it. You treat power like a signal. You run thick traces or power polygons on the signal layers, layer 1 and 4. Don't waste a full internal layer on it. Use that internal layer for a second ground reference instead.
That is a huge shift in thinking for a lot of people. Treat power like a signal.
Until you get to higher layer counts, yes. When you have 8, 10, 12 layers, sure, bury the power. But on a 4-layer board, you need that copper for ground. You cannot sacrifice your return path for the convenience of a power plane.
Which is the perfect segue.
Yeah.
Let's talk about the big leagues, the 6-layer stack-up.
Now we have freedom. Now we can really start to engineer the behavior of the board.
The source outlines 2 specific stack-ups for 6-layer boards. Let's look at the first one, which they describe as an EMC powerhouse.
This is stack-up 1. The structure is L1, signal. L2, return reference plane. L3, signal. L4, signal. L5, return reference plane. L6.
Signal. Okay, let me visualize that. Signal, ground, signal, signal, ground, signal.
Correct.
So we have 4 signal layers, 1, 3, 4, and 6, and only 2 ground planes at 2 and 5.
Yes.
Doesn't that violate the rule? Layer 3 is a signal layer. Its neighbor is layer 2, ground, good. Layer 4 is also a signal layer. Its neighbor is layer 5, ground, good. But wait, layer 2 is acting as a reference for layer 1 and layer 3.
Yes.
And layer 5 is referencing layer 4 and layer 6.
Precisely.
How does that work? How can one piece of copper be the reference for 2 different signal layers simultaneously without the signals mixing? I mean, won't they interfere if they share the same ground plane?
This is where it gets really interesting. This is the magic trick of the 6-layer board. It relies on a phenomenon called the skin effect.
The skin effect. I remember this from electromagnetics class.
Right.
I usually hear this in the context of AC resistance. Like, oh, at high frequencies, the wire resistance goes up because the current gets pushed to the outside.
That is exactly what it is. But usually we think of it as a bad thing, a loss mechanism. Oh no, my effective cross-section is smaller, my resistance is higher. Here, we are using it as a feature.
Ow.
Think about the copper plane on layer 2. It has a thickness. Standard copper is usually 1 ounce, which is about, what, 35 microns thick?
Right, 35 microns, it's thin.
But at high frequencies, say 100 megahertz or 1 gigahertz, the skin depth of the current is extremely small, maybe a few microns.
Okay.
So the return current for layer 1, the top signal, doesn't flow through the whole thickness of the copper. It flows only on the top surface, the skin of layer 2.
It skims the top.
And the return current for layer 3, the inner signal, flows only on the bottom surface of layer 2.
Wait, so the currents are on the same piece of metal, but one is on the roof and one is on the floor.
Exactly. Because of the skin effect, the current density drops to near zero in the center of the conductor. The changing magnetic fields induce eddy currents that push the flow to the periphery. So effectively, the top of the copper and the bottom of the copper are electrically isolated from each other for high-frequency signals.
That is wild.
The currents do not mix, so you effectively double the utility of your reference planes. Layer 2 serves two masters, but because of physics, they never meet.
That is incredibly cool. So that's why this configuration works so well. You get 4 signal layers, but they all have a pristine reference path.
Correct. And in this stack up, you would route your power on the signal layers, just like in the 4-layer example. Or maybe pour some power on parts of layer 3 and 4, keeping away from high-speed lines.
But sometimes you need real power, like heavy current, or a very complex power delivery network, a PDN for a big FPGA where you have 5 different voltage rails.
And that's when you switch to stack up 2, the high-power, low-impedance PDN configuration.
How does that one look?
It's L1, signal, L2, return reference plane, L3, power, L4, L5, return reference plane, and L6.
Signal. Ah, I see. So you sacrifice the 2 inner signal layers, 3 and 4, and turn them into dedicated power planes.
Yes, but notice what we kept. L2 and L5 are still ground. So L1 and L6, the signals, still have their adjacent references.
So the outer signals are safe.
Yes, and L3 and L4 are power. This creates a very stiff, robust power delivery system. You can carry huge currents. And because L3 power is next to L2 ground, you get that interplane capacitance we talked about, which helps filter the power supply.
But there's a warning here, too, about polygons.
Yes, the polyon warning. The source advises using solid, homogeneous planes for these power layers.
Meaning, don't chop them up into a puzzle.
Exactly. Sometimes a designer tries to get clever. Oh, I'll use layer 3 for 5V, but over here in the corner, I'll pour some 3.3V and maybe a little 12V island over there.
Mixing voltages on the same layer, it saves space.
It saves space, but it's dangerous. When you have different polygons on a single layer, you create gaps between them.
And if a signal on an adjacent layer crosses that gap.
We're back to the discontinuity problem. Even if the adjacent layer is power, if any high-frequency energy is coupling to it, that gap becomes a slot antenna.
And also, I imagine having 12V ripple right next to 3.3V logic supply on the same plane isn't great.
It's not. Split power planes can generate significant common mode noise. If you connect a cable to that board like a USB or Ethernet cable, that noise will ride out on the cable shield and you will fail radiated emissions.
So the advice is, 1 layer, 1 voltage.
Ideally, yes. Dedicate the plane. If you need multiple voltages, try to generate them locally with point-of-load regulators or route them as thick traces on signal layers. Keep the plane solid.
It really all comes back to that geometry, doesn't it? Solid planes, unbroken paths.
It does. Geometry dictates physics. You can't cheat geometry. You can try, but the spectrum analyzer will catch you.
Because if I change the distance between layer 2 and layer 3 to avoid crosstalk like we discussed in the 4-layer shielded model, that changes the impedance of my traces, right?
Everything is connected. If you change the dielectric height, you change the capacitance, which changes the characteristic impedance. So you'd have to change the trace width to compensate.
So we've covered a lot of ground today. Or should I say, a lot of stack up.
Yes.
Let's try to summarize the key takeaways for the listener who is maybe looking at their next board design right now and feeling a little paranoid.
Sure. Let's break it down. Number 1, signal propagation requires a loop. It's not just a wire, it's a signal and a reference. You must design both paths. Number 2, the reference must be adjacent. You need a return reference plane, an RRP, right next to every signal layer, no exceptions for high speed.
Number 3.
Number 3, 2-layer boards require discipline. Keep the bottom layer as solid as possible. If you must route on it, keep it short and check your vertical alignment. Don't build moats. Number 4, 4-layer boards. Beware the power plane. It's a trap. Use the inner layers for ground references or use the shielded approach. And stitch your grounds together.
And finally,
Number 5, 6-layer boards. Leverage the skin effect. It allows you to use one ground plane for 2 signal layers without mixing them. That is your superpower.
And if you follow these rules,
You contain the fields. You stop turning your PCB into an accidental radio. You pass EMC certification.
which is the ultimate goal, we want to ship products, not debug them in a test chamber for 6 months.
Amen to that.
Before we go, I want to leave the listeners with one final thought. Something that really stuck with me from this deep dive.
What's that?
It's the skin effect. We spent so much time in engineering school learning about how skin effect increases resistance. It was always presented as a problem. Oh, at 1 gigahertz, your wire resistance is terrible because of skin effect.
True. It was always the villain.
But here, in the context of a PCB stack-up, it's the mechanism that allows us to pack more density into a board without corruption. It turns a limitation of physics into a design asset.
That is a beautiful way to put it. Engineering is often about taking a physical constraint and flipping it on its head to make it work for you. That's what good design is.
Yeah, exactly. So if you are listening to this and you're realizing, wow, I have been guessing at my stack-ups, or I just use whatever the fab house defaults to, it might be time to stop guessing.
Start engineering your compliance.
If you want to dive deeper, really master these concepts beyond what we can cover here, you need to go to the source.
Visit freezeelectronics.com.
You can learn more there, or even join the Fresu Electronics Academy. If you want the deep training, that's where you go.
Highly recommended.
Thanks for listening to this deep dive. Go check your stack-ups. We'll see you next time.